everybody. This is Mr. Hunt speaking. We're going to be covering lesson 5 in video format, just to see as a test if I can make video formats for classes, see how you guys like them. You can follow along. I'll try to get it out as soon as possible. All right, we're going to start with lesson 5. It has 4 parts: 5A, B, C, and D. We're going to start with 5A and exponents and radicals. As you see from the screen, it says key things to remember about exponents and radicals. Right? It's going to be the square root of a number factored twice is that number. Not too much of a hard concept, I don't think. I'm going to set this, make sure it's okay. If you take a number like 7 and you want the square root of that multiplied by the square root of 7, ultimately you've just gotten rid of your square roots and your answer is 7. Easy enough? Alright. I'm going to make this thickness down a little bit. Alright. Also, second point, we're going to add the exponents when you're multiplying powers of the same basis. So if you see, if you have 4 to the power of whatever times 4 to the power of whatever, let's go with an example of 1/2. 4 to the power of 1/2 times 4 to the power of 1/2, you're simply just going to add these two together. 1/2 and 1/2 equal a whole. 4 to the 1 is going to be 4. The exponent 1/3 can be used to indicate the cube root, and 1/4 to represent the 4th root, and 5th and 6th and 7th, so on and so forth. Alright, not a hard concept. Moving on, if we were to look down here at this little example of 3 to the 3rd times 3 to the 3rd times 3 to the 3rd. Well, you got 3/3. You're going to end up with a whole again. Answer's going to be 3. This works, so on and so forth. Alright, example 5.1 asks us to simplify the square root of x cubed y times the 4th root of xy cubed. Another thing to remember over here, I started out, is the square root of a number is going to be equal to that number raised to the 1/2 power. Transversely, we got the square root, or the cube root, or the x root of a number will be that number to the 1 over the x root that you're using. So if this x is a 3, it'll be a 1/3, and so on and so forth. Step 1 in this process is going to be replace the radicals with parentheses and fractional exponents, and then multiply the exponents where indicated. So in this case, I've removed the radicals here. We'll replace those with parentheses, right? And big plus, fractional exponents. So this was the square root. If there's nothing here, it's indicated it's automatically a square. So fractional exponent would be the 1/2, hence the repeating of this rule up here. All right, and this one's the 4th root, so it will be raised to the power of 1/4, right? We're going to end up with x to 3 over 2 times y to 1 over 2 with x to 1 over 4 times y to 3 over 4. Second step will be rearrange the like bases and simplify by adding exponents. So we'll take the x's together. We're going to end up with a 3/2 and 1/4, I believe. Over here we'll have y to the 1/2 times y to the 3/4. Remember, they have like bases. Now we're just going to add the fractions together. We have to get common denominators. This will end up being 2 over 4. This will end up being 6 over 4. Now we add those together. We'll end up with x to 7 over 4, y to 5 over 4 for a final solution. All right, moving along to example 5.2. Wants us to simplify this big mess. All right, a to the x over 2 times y to the 2 minus x to the 1/2 over a to the 3x times y to the negative 2x. All right, so the first thing we're going to do is just need to inverse these denominators here so we can get it all up into the numerator. We're going to simplify and write all exponents in the numerator. To do that, just inverse these. So it's a positive 3. We'll turn it into a negative 3. And then obvious here, 4 plus the 2x here. You'll multiply that over itself. Ultimately, this thing is going to equal 1. So we're putting everything up into the numerator as the step requires. From there, we're going to have a to the x squared times a to the negative 3x. That's this one and this one. And then we'll have y to the 1 minus x squared over y to the 2x. Now, we did have some problems figuring out how exactly y to the 2 minus x to the 1/2 simplified down to 1 minus x over 2. So I wrote that down right here. What we'll do is we'll zoom into this. All right, so we remember that if you have a base raised to an exponent, which is raised to an exponent, both your exponents will be multiplied together. So you'll take your y to the 2 minus x over half will turn into 2 minus half times 1/2. Ultimately, we'll break out into, distribute that in. Half of 2 is 1, and half of negative x will be a minus x over 2. Hope you guys can see that. All right. Ultimately, we will go on to step 2. It gets a little bit involved with all this math. I've got it grayed out here so we can go over it together. Let's see if I can't put that into a lower. All right. So when we get our a times x over 2 times a to the negative 3x, well, we're going to have to add these together. So we're going to put this over 1 to get a like denominator, right? Times 2 over 2. We'll get a negative 6 here and a 2 on the bottom. That's gone. That's gone. All right. Ultimately, you'll end up having your a negative 6x over 2 times a plus x over 2. Negative 6 plus an x is going to equal your negative 5 x over 2. For the y's, we ended up with a y with a 1 minus x over 2 times a y to the 2x. Well, that's going to be over 1. That's going to be over 1. We're going to add this to this. All right, so we're going to have to get common denominators, which will be 2. 2 over 2 gives us a 4x. 2 over 2 over here gives us a 2 over 2, still a 1. We're going to be distributing this in. So when you distribute that in, you're going to end up with 2 over 2 minus x over 2 plus 4x over 2. Ultimately, y is going to be your 2 plus 3x all over 2. That's your new exponent. All right. Put it all together. A to the negative 5x over 2 times y to the 2 plus 3x over 2 parentheses, and that is done. Example 5.3, we're going to simplify x to the negative 2 plus y to the negative 2 all over xy to the negative 1. Step 1, very easy. Eliminate negative exponents, then add the two expressions in the numerator. All right, easy day here. If you remember, if we have a negative exponent, you're just going to have to make it positive and put it all over 1. So that's what we've done here. 1 over x squared plus 1 over y squared over 1 over xy. And now we've gotten rid of all of our negative exponents. Don't want those. And then we're going to have to go ahead and add all the expressions into the numerator. Well, in order to do that, we're going to add all these in the numerator. by finding like denominators. This one right here will be y squared. This one right here will be x squared. Ultimately, we end up with y squared plus x squared over x squared y squared. That's all going to be over 1 over xy. So step 2 is going to finish by multiplying above and below but the reciprocal of the denominator. Let's see if I can use my tools here. I'm going to open this, see if that captures. Nice. All right, cool. And duplicate that. All right. And I'll bring it down here somewhere. Perfect. Okay. Click out of there. All right. What are we going to do? All right, we're going to finish by multiplying above and below the reciprocal of the denominator. The reciprocal of the denominator is going to be this. Flipped. Easy day. xy over 1. Right? And then xy over 1. This is my favorite part right here because we just start doing eliminations here. That's gone. That's gone. That's gone. That's gone. All right. And then we have an x on the top here and 2 x's on the bottom, so that gets rid of one of the x's. So this is now gone, while this is gone as well. This y will be gone and this square will be gone, ultimately leaving us with a final answer of y squared plus x squared over xy. And that one's done. Simplify the 3 to this times the square root of 3 halves minus 4 times the square root of 2/3 plus 2 times the square root of 24. For these types of problems, they want us to change the form of radicals and use multiplication as necessary to rationalize the denominators. And that's the key thing right here, right? Let's go ahead and rationalize these denominators. It's not hard to do. We will multiply these denominators here by something we can get rid of. And we've got a square root of 2 times the square root of 2. That'll equal 1, so we're good. Over here, what do you think it'll be? I'm betting you it'll be this one right here. Yep. Square root of 3 times this over the square root of 3. This one right here is already good, but we can see already that this is factored out. The 24 is square root of 4 times 6. This is a perfect root, so that'll be 2 times 2 square root of 6. We'll carry that down here. All right, let's move up a little bit, see what we have. After you rationalize these denominators, right, and multiply as necessary, you're going to end up with rationalizing. You're going to have a 3 times the square root of 6 over, what's our rule? Square root times square root, same. It's just going to be that number, so it'll be 2 with no square root. Over here, same deal. All right, 2 times 3 is 6, all over, oh, big fat 3. And then over here, rationalize that out. We'll just bring it down to 4 square roots of 6. Okay, finish by finding the common denominators and adding. Step number 3. You know, I might want to jump up a thickness here. Perfect. Okay, so in order to do this, we're going to be multiplying common denominators here. In order to get this 2, we're going to be multiplying it by 3. All right. This one, we're going to have 4 square roots of 6 times 3. We're going to multiply that thing by 2. And over here, we're going to have 4 square root of 6. That'll be over 1. Multiply that bad boy by 6. All right. What's that going to give us? All right, so we're going to have 9 square roots of 6 over 6. Right? Minus, what are we going to have now? 8 square roots of 6 over 6 plus, oh, is that 24? 24 square roots of 6 over 6. Should have like denominators. We got 9 minus 8 is 1. 1 and 24 is 25. So we will have 25 square roots times the square root of 6 over 6. That can't be reduced any further, so we are done with that one. Example 5.5, they want us to simplify that. All right. I don't like this one. All right, I can see easily we got parentheses here. We're going to use the FOIL method. First outers, inners, lasts, right? So we have the firsts, the outers, the inners, the lasts. Square root of 2 times 1. Anything times 1 is itself. So we're going to have the square root of 2 as our first term. Outers. Firsts, outers, it's going to be this minus the square root of 2 times the square root of x. Now we're going to have plus the square root of x times 1, anything times itself, so we're going to have plus the square root of x and square root of x times the square root of x, negative square root of x. We're going to end up having a minus x, getting rid of our radical. All right, now we're going to factor the two middle terms. This will be term number 1. This will be term number 2. This is the part I don't like because it says note the coefficient of the second term is the sum of, and if it's the sum of 1 minus 2, right? How do they get that? All right, so this is on the right. I don't like things being on the right, so I put them on the left. We're going to bring this common term. These are the common terms, or the commonalities between the two middle terms. So 1 will come out and then factor inside in order to get our answer. And in order for this to happen, we'll end up being times 1 and then a minus square root of 2. Alright, we'll have the square root of x times the negative square root of 2 square root of x when factored out. Alright, that's them factored out. So we'll end up with the square root of 2 minus 1 minus the square root of 2 times the square root of x minus x. Okay, clear as mud, moving along. Lesson 5 at 5B, complex numbers. And in math, the letter I is going to be used for the positive square root of negative 1. So I equals the square root of negative 1. Listen, I is a shorthand symbol that's used, first used by the Swiss mathematician Euler, and he lived from 1707 to 1783. Square roots of a negative number can be written as a product of a real number and I. You can see down here we've got square root of negative 15 can be rewritten as square root of 15 times negative 1, or the square root of 15 is equal times the square root of negative 1 will be equal to the square root of 15 I. So I equaling the square root of negative 1, you just factor any negative out. All right, well, coming up here we have, since I is equal to the square root of negative 1, then I squared is equal to negative 1, because remember our rule, rewritten here, anything square rooted times itself will be itself with the square root gone. So I squared equals negative 1 because the square root of negative 1 times the square root of negative 1 equals, you guessed it, negative 1. A complex number is made up of two real numbers, a and b, and the letter I. So a plus bi. Complex number is said to be in standard form. And complex numbers have a real component, A, and an imaginary component, B. I've color-coded these here. So A is your real component, B is your imaginary component. You can see it real clearly though, the imaginary component usually has that little I in there, right, for an imaginary number. I put standard form in green. That'll be important later because your answer can be wanting those to be in standard form. So if we tracking over here, we've got all of these are considered complex numbers in standard form. We have 4 plus 2i, 3.01 minus the square root of 2 over 3i, still following the same format, right? Which is a plus bi. You look at C and D, however, you just got 4.06. Well, they rationalize that by saying it can be imagined that 4.06 plus a 0 times I. And then over here on the transverse, you can have 0 plus 3i. So that's your real component, and 3i is going to be your imaginary component. So theoretically, anything can be an imaginary component. Example 5.6, I want us to simplify 3i cubed plus 2i to the 5th minus 3i plus 2i squared. This is pretty simple here. We're just going to go ahead and expand and pair the I terms, right? So you've got 3 i's here, I. Well, okay, so it's 3 times I, and then you pair up 2 of them, right? So 3i times I. And then 2i, and then we have 5 total here. So 2 pairs, 2 and 2 and 1 make 5. So they're all paired up. And you can turn all of these double I pairs into negative 1s later on. That's the second step. Replace each pair of i's with negative 1. You'll end up with 3i times the negative 1 plus 2i times the negative 1 times the negative 1 minus 3i plus 2 times the negative 1. You simplify all of that out, right? And you write the results in standard form. There's that green color again. Your standard form, you have negative 3i plus 2i minus 3i minus 2 is equal negative 2 minus 4i. But is that in standard form? No. Well, no, it is. On to example 5.7. A little bit lengthy, but you can see what happened here. We take all of this negative 3 stuffs and we're going to translate that into 3 times a square root of negative 1, which ultimately will factor down to an I. So when doing these, you do have to realize that be on the lookout for something like a 3 and an I, that this right here is not above, right? That's a no-go. They're usually on the outside of your radical. So you use the I notation, right? So once you get rid of all of these and do your simplification, you'll end up with all of this, right? Square root of 3i times 2 plus 3 times the square root of 2i times 3i plus 4i plus 4. We simplify the 2 square root of 3i to minus 2 square root of 2 plus 4i plus 4 and finish by grouping real and imaginary parts. Doing that, you can see that we had 3i times 2 plus 3i times the square root of 2 times I times 3i plus 4i plus 4. This reduces down. This 2 comes over to the left. Let's see if I can't write this, so I'm going to change my color up. Alright, 2 over here times 3i. Over here we're going to end up with 9 times the square root of 2 and then you're going to have your i's, which will turn into negative 1. Pair of i's equals negative 1, so that's going to change your sign. Don't forget to change your sign. And plus your 4i, 4. Simplify all this down, you'll end up with 4 minus 9 square root of 2 plus the square root of, 2 times the square root of 3 plus 4. And you can see how they just factored your like terms right here. Your i's, they got factored in because they both had one common. So square root of 2, or 2 times the square root of 3 plus 4, all times I. Works out to be the same. Ultimately, it's just this making it inverse. So it would be a negative at the end of the day, whatever the number turns out to be. All right, moving on to 5.C, areas of similar geometric figures. You see that the ratios of the areas of similar two-dimensional geometric figures equals the square of the scale factor between the figures. The book will tell you this is easy to say, but it's hard to conceptualize or visualize whatever. I disagree. It's pretty easy to see. You have example 5.8 right here. It tells you the scale factor between two rectangles is 4. What is the ratio of the areas? Well, let me bring this up into view here. You see you have one little pink box here, and then you have 16 pink boxes here, right? Because there's only one here. Now there's 16 because this was just cut and paste 4 times up and 4 times to the right. So you end up with a 4 by 4, which is 16. Very simply, 1 to 16 ratio, or 16 to 1. The formula they give us is just as easy to understand. You have a width and you have a length, and you have a scale factor given to you as a 4. So it's 4 W's and then 4 L's. So the area 1 will be length times width. The area 2 will be 4L times 4W, and that'll be equal to 16 LWs. You put area 1 over area 2, you'll have LW over 16 LWs. This is a 1, so your answer is 1/16. So ratio can be said as 16 to 1, or it can be 1 to 16, left to right. Pretty simple concept. Example 5.9, they have the radius of one circle is r, and the radius of the second circle is 3r over 5. So what is the ratio of the area of the first circle to the area of the second circle? Okay, well, we have A1 over A2. That's pretty easy. And then we just plug in our area for a circle. That's pi r squared, right? We have that written here, pi r squared over pi times r squared. In this case, it's the second circle, which is 3r over 5. This r is not representative of radius. It's just a capital R variable. All right, so with that being said, you can do your math, and you'll end up with, I already crossed this out here for you, but you'll have 9r over 25, and that r squared will be there, and all that will be multiplied by pi. And then you'll have, up on top, you'll have a pi r squared. And then you can start to eliminate. So that r squared and r squared make a 1, that pi and that pi make a 1, and you end up with ultimately 1 over 9 over 25. And to get rid of this, we just inverse these numerator denominator. Ultimately, you'll end up with 25 over 9 for a final answer of your ratio, right? Of the ratio of the areas of the first circle to the second circle. Okay, last but not least, we're on to 5D, diagonals of rectangular solids. This is also super simple concept. You know the Pythagorean theorem, you're good, all right? You're going to use the Pythagorean theorem twice to find the formula for the length of the diagonal in your rectangular solids. All right, so example 5.10, they tell us to find the length of the diagonal that connects corners B and H in the rectangular solid below. I went ahead and created a little solid for you here. I color coded that diagonal underlined with green so you can see it pretty easy. B to H is what ultimately they want to do. So it's a two-step solution to this type of problem. Again, we're going to use Pythagorean theorem twice to figure it out. You're going to find the length of BG. Okay, BG is down here, right? We're going to remove the whole base, and that whole base is going to be a rectangle FBCG. And we're going to get the diagonal between B and G, right? Because we have two givens. We have two legs given. We're just lacking a hypotenuse, which is BG. We can use this theory to go ahead and plug the Pythagorean theorem in to get our length of BG. You can see that BG squared is going to be equal to BC squared plus GC squared. Factor that all down, they'll give you a BG is going to be equal to the square root of x squared plus y squared. Now you have found the length of BG. Now that's going to be one leg, and HG is going to be another leg for the hypotenuse of BH, which is your ultimate goal of finding, right? So step 2 would be to plug in the BG as one of your legs, to HG, another known leg, to find your hypotenuse. We do that and we'll end up with the square root of x squared plus y squared plus z squared will now equal your BH squared. You factor all that down and you're going to end up with BH with a length of the square root of x squared plus y squared plus z squared, and we'll consider that solved. Moving on to example 5.11, which I might be mistaken, but I'm pretty sure in the problem set they had the exact same question. So you're going to find the length of the diagonal that connects corners A and C in the rectangular solid below. They changed the things up, put some numbers in there instead of XY variables. But I color-coded what you're trying to get. A to C is what you're trying to get. Step 1, remember, we're going to remove that bottom base. Take what's known. We have a B and a C is what we're looking for. They're giving us a 2 and a 3. Plug all that in. Our BC hypotenuse will be the square root of 13. And that becomes the second leg that you needed for another right triangle to find the hypotenuse, which is your ultimate goal of AC, or the diagonal of the right solid. So you plug that in, it's the square root of 13 squared. You move it down, you have 13 plus m squared. AC is ultimately going to be equal to the square root of 13 plus m squared.